We now turn to looking at mistakes in causal reasoning. That's to say, things that can go wrong when engaging in causal reasoning. Now, there are various reasons, as we saw, to reject causal explanations. An explanation might be unduly complicated, or incompatible with known facts or theories, or vague, ambiguous, or circular, or it may be inherently untestable, and all of these would be bad. What we'll turn to now is some particular problems with causal reasoning, including various fallacies. The first one we'll take a look at is the dreaded post hoc ergo propter hoc, which translated into the English would be after this, therefore, because of this. The mistake being made here is when someone infers that because one thing immediately occurs before another thing, that the first thing causes the second thing. For example, a person might pray for someone's recovery, and the person might recover. And the person who prayed might infer that their praying cured the person. Now, it may be true the praying cured the person, but merely because the person prayed, Sally prayed for Bill and Bill was cured, doesn't prove that her prayer cured Bill. Or another example, suppose that Elvis buys a new sound card for his computer, and then it starts crashing, and he concludes the card must be the cause. Well, that'd be too quick. I mean, it may be the cause, but just saying, well, this happened, I put in this new card and my computer started crashing, that would be, reasoning too rapidly. As a final example, suppose a person had a heart attack while running, and then a second one while recovering, and then they go on a special diet, say the marathon diet plan. They recover go on to run 20 marathons. Now, if they infer that the diet caused their recovery, maybe it did, maybe it didn't. But just simply saying, well, I went on this diet and I never had another heart attack and ran lots of marathons, hardly proves that that's the cause. It could be something else entirely. Now, the form of this, to be a little more technical, is as follows. Since it's a fallacy, it's actually an argument, albeit a bad one. And the form is this. Premise 1, A's immediately precede B's, or this particular A precedes this B. Conclusion, therefore A's cause B's, or this particular A caused this B. And this, of course, is a mistake because the mere fact that one thing happens before another does not prove there's a causal connection. There might be. The person could actually be saying something true, but the mere fact that one thing happened before another is not sufficient grounds for inferring that it is the cause. The second fallacy associated with causation is the come hoc ergo propter hoc, which is basically with this, therefore, because of this. The idea occurs when someone believes that simply because two things are correlated, that one thing must have caused another. For example, suppose someone noticed that ice cream sales, when they increase, there's also an increase in drowning deaths, and they inferred that ice cream was killing people. Well, obviously that would be, pretty unreasonable. It's just mere correlation. What's the actual, factor involved? Well, obviously enough, when the temperature increases, people eat more ice cream, they also swim more, and unfortunately, as people swim more, the number of deaths by drowning increase. Now, the form of this, be a little formally, again, it's an argument, but a bad one, a fallacy. The first one is premise 1. A's are correlated with B's. Conclusion, since they're correlated, A's cause B's. Now, once again, we actually have a saying for this, correlation is not causation. So why are these two fallacies actually fallacies? Well, the reason is as follows. It's because they don't establish the improbability of three possibilities. And these are things that need to be considered when assessing causal reasoning. The first possibility is this. Basically, it's coincidence. It should be considered that the connection between A and B is purely coincidental. For example, suppose somebody, notices their cats are acting kind of odd. And a few days later, there's an earthquake. And they conclude that the cats, were predicting the earthquake, that it was causing them to, act strangely. Now, people actually do have the view that animals can predict earthquakes, and of course, not surprisingly, scientists looked into this because it would actually be pretty handy if, just as dogs can sniff out bombs, they could sniff out an earthquake. However, they found there's no actual causal connection. Now, what people do, of course, is they remember cases where their pets acted strange and something unusual happened. And they forget about all the times their pets acted strange and nothing happened. And so it could be a pure coincidence that the cats are going crazy and then there was an earthquake. In fact, the cats probably went crazy lots of times and when there was not any earthquake. As another example, suppose somebody buys a new computer game and they try to play it and the computer keeps locking up. And they conclude, well, the game must be causing the trouble, and they throw it away. Well, that'd be a little bit too quick. It just could be pure coincidence. As another example, I was opening up my computer to adjust some things, and I pulled up the video card, cleaned it out, cleaned out the fan, set it back in, and then when I rebooted my computer, it said, the date and time were wrong, and my BIOS was also apparently incorrect. And it's like, what the heck? And so I figured, well, maybe, the video card caused the problem. Because obviously I took it out, cleaned it, put it back in. That was the change, could be the cause. And then I, tested everything, and the video card worked fine. It was just that the startup was kind of messed up. And then I thought, well, the obvious possibility is since the BIOS is kept by kept going by the battery on the motherboard, I thought, well, maybe something happened to the battery. And I checked, pulled the battery, put in a new one, worked fine. So it just was a matter of pure coincidence that after taking out the video card and the battery just went out at that time. But, I considered the possibility that the video card was just a coincidence, when the actual cause, investigating further, turned out to be the battery just happened to go bad at that time. And so it was just a coincidence. I was opening up the case and messing around with it at that time. Second possibility, it could be the case that both A and B result from a third underlying thing. This is known sometimes as ignoring a common or underlying cause. For example, going back to the example I gave earlier about ice cream sales and drowning deaths. As ice cream sales increase, drowning deaths increase. But you don't really have to be worried about the ice cream because it's the warm weather that's causing both of these to occur. Third possibility, known as reverse causation. It could be the case that a person is simply inferring that, A causes B, when in actuality, B caused A, rather than A causing B. And it's the failure to consider the possibility that creates the problem. For example, suppose somebody learns that homeowners tend to be more responsible, have greater financial stability, greater income, commit less crimes than non-homeowners. And they conclude the way to deal with all these problems is to get more people to become homeowners. Now, while homeowning may have an effect on people's behavior, this is obviously reverse causation. It's not that having a home makes people more responsible or gives them more money. It's rather that in order to have a home, you've got to have more money to pay for it in general. And of course, in general, you have to be somewhat responsible to be able to get a house, unless someone just happens to give a person a house so they inherit it or win the lottery. Another example would be with video games and violent movies. It's inferred that, well, surely these video games and violent movies cause violence, without considering the possibility that maybe it's the fact that people are violent that causes them to like violent video games and violent movies that would generate this mistake. Now, in the case of video games, movies, and gun violence, or any violence of any sort, that's a matter of considerable controversy. After all, to simply say, well, we got movies, we got, gun violence, so the movies cause it, would be too hasty, because it could be reversing causation. But then again, perhaps not. But what is required is, of course, that maybe the causation is right, but simply saying, well, the one thing and another doesn't prove that the movies caused the gun violence. We must consider the possibility that the reverse could be true. So those are the first two fallacies, the post hoc the come hoc, ergo propter hoc. The basic idea with the post hoc is that a person infers that because A occurs before B, A must cause B, and the come hoc, ergo propter hoc occurs because a person infers incorrectly that because A correlates with B's, that A must cause B. Now, another mistake involves confusing conditional probabilities in medical tests, which suggests the authors of the text had a scare for the medical test. Now, the probability that one thing, let's say X, given Y, is distinct from the probability of Y given X. For example, the probability that the toilet is leaking, given that there's water on the floor, is different from the probability that there is water on the floor, given that the toilet is leaking. Now, people sometimes assume that the probability they have a medical condition is high if they score high on a test for that condition. But what they fail to take into account is the fact that testing positive for a medical condition, or a condition at all, is the effect of that condition, not the cause of that condition. For example, suppose there's a test for bladder cancer, and it's 90% accurate. That means that 9% of those who have cancer, the cause, will test positive, the effect. To know a person's actual chance of having the condition, say bladder cancer, you need to know a few things. First thing is the percentage of false positives. In other words, how many times will the test result in a positive result when the person doesn't actually have the cause. And also the base rate, the frequency of the cause. For example, suppose you get a test that's 90% accurate. Well, that means that 10% of those who test, let's say for bladder cancer, will test positive and not have it. And suppose the base rate in the population is 1%. Now, if you test 1,000 people, if you have 1,000 people tested, 10 of them will have bladder cancer, because that's 1%. 9 of them will test positive because the test is 90% accurate. Third, 990 of them will not have bladder cancer, because 10 will, the rest won't. Of these 990, given that the test is 90% accurate, 99 of these people will test positive. So, out of 1,000 people with a test that's 90% accurate, 108 will test positive, but only 9 of them will have bladder cancer. So, a person who tests positive doesn't have a 100% chance of having bladder cancer. They don't even have a 90% chance of having bladder cancer. They have an 8% chance of having bladder cancer. This is not to say that a person should just dismiss medical tests, obviously, but that there was a positive test for a 90% accurate test is not a guarantee that one has the condition. And a mistake being made here is, of course, to reverse cause and effect. Now, a second common problem involving statistics is people often overlook statistical regression. Here's the idea. Statistical regression, or sometimes referred to as regression to the mean, refers to statistical measurements of mean values of populations. And measurements of the population tend to regress to the mean. Some examples. The average height of a 40-year-old man in the US is 5 feet 10 inches. Suppose you measure the average height of the children of 40-year-old males, whose average height is over 6 feet 5 inches. The average height of these kids will be closer to 5 feet 10 inches. This explanation doesn't involve cause and effect, because the fathers of usually large children are apt to be shorter than their kids. Another example. Suppose you have people guessing on a true-false test. Some people will score above 50%, some below, but the average will be about 50%. Now, suppose you take those who scored above 60% and then you have them guess on another test. What would probably happen is, most likely happen is, the results would be closer to 50%, and you can test them again. So the idea is basically there'll be a regression to the mean. So you can imagine this, taking the true-false test example, you can imagine having people in the class guessing on a true-false test. And some people will score above the statistical average. They might score 60 or 70, or someone might even get them all right by pure chance. And if we have them take, test after test guessing on it, the results will regress to the mean. In other words, they'll tend to get 50% in the long run. Another example. Suppose you have an athlete who performs above average in one game or season. Now, typically, as people know from sports, they usually don't repeat that the next game or season. Now, people sometimes explain this as a loss of concentration due to success, or other athletes start focusing on the competition, or there's a coaching change, etc., which could be true. Or it might just be statistical regression. In other words, the person has an unusual game or season, and then they go back to the normal statistical results later, without there being any unusual causal factor at play. Now, regression to the mean can happen pretty much in any of those cases. As another example, suppose you've got an occupation like we have we had our troops in Iraq and Afghanistan, and suppose the number of troops killed in one month was unusually high. The next month, it's likely to go back to the mean without being caused by some other factor. And so in considering results like that, it's always important to consider the possibility of statistical regression. In other words, to infer, suppose we have like high troop casualties one month, and then they implement some new plan and the casualties drop, rather than just leaping and saying, the new plan was successful, it's worth considering that the results of the previous month were unusual, and the plan did nothing. The results just reversed or regressed to the mean. Or as another example, suppose you have heart patients, and you take those with the average highest blood pressure, and you give them a medicine and retest them. Well, the second average will probably be closer to the mean. This is not to say the medicine had no effect, but it could be the case that there's simply a regression to the mean. Which is why it's always important when testing stuff to test multiple times. And to use a final example, from one of my neighbors, she was trying to sell her house, and she, the potential buyer wanted to have a radon test done. And the first test was done, and a result of 4 or higher is considered bad. And the test was done, got a result of 4. And so she paid to have the test redone because it's close to the safe level. And in the test, this term turned out to be an 8. And then another time turned out to be something else. And so this illustrates the importance if you just do like a test once or even just twice for a short time. It could just be giving a result that's inaccurate. And so you'd want to test many times because the unusual results could be due to just some random factors, poor testing, unusual conditions, etc. Which is why it's important to get a lot of results as opposed to just focusing on 1 or 2 unusual results. The next thing we turn to is something we saw before in the chapter on fallacies, namely the proof by absence of disproof. Here's the idea. Sometimes it's claimed that the absence of disproof for a causal hypothesis increases the likelihood the hypothesis is true. For example, a person might say, no one has proven that drinking tea with honey won't prevent colds, or no one has conclusively shown that vaccines don't cause autism. Now, cases do arise in which people do try to disprove a causal claim. For example, the claim that vaccines cause autism. That was extensively studied, and it was found out rather conclusively that they do not, in fact, cause autism. But again, it's inductive, and so we could still be wrong. Now, but in general, if you can't disprove a causal claim, it only leaves intact whatever reason already existing for thinking the hypothesis was true. The absence does not create a new reason for thinking it is true. For example, if someone says, you can't prove that tea with honey doesn't cure colds, maybe that's true, but the mere fact that you can't disprove it, show conclusively that it doesn't do it, doesn't prove that it is true. So obviously, the fact that one can't disprove a claim doesn't show that it's true. An example I was used to illustrate this is the invisible unicorn example. Back when I was a kid, in grade school, people hit on the idea of the invisible unicorn. A kid would say, "I've got a unicorn." And of course, all the kids would go, "Wow, I want to see your unicorn, your unicorn." And the person would say, "Well, he can't see me; he's invisible." And it would be all like, "Oh." And then some smart kid would try to reach around and try to find the unicorn by touch. And the person would say, "Oh, you can't catch him; he's too quick." And so every time you tried to disprove the unicorn, the smart kid would come up with some reason why you couldn't. He was too quick or too small or whatever. And of course, you can never disprove that unicorn because there's nothing that can disprove it. Because every time you try, the person who claims they would use a unicorn says, there's some reason why you couldn't disprove it. But obviously, that doesn't prove there are invisible, super fast, untouchable unicorns. Because the burden of proof is on the person who claims there's such a thing. Now, our next problem or mistake is something we saw before, namely the appeal to anecdote, sometimes known as appeal to anecdotal evidence, sometimes known as anecdotal evidence. This is a fallacy in which data that offer reasonable support for a general claim are ignored in favor of an example or two that do not. Basically, the person tells a story, an anecdote that goes against established data, and they reject the data in favor of a case or two that goes against it. Now, in a causal context, this fallacy is committed when a person tries to prove or disprove that X is a causal factor for Y by citing an example or two of an X that did or did not cause a Y. For example, if someone says that red wine prevents colds because Bill drinks red wine with every meal and never gets a cold, well, that hardly proves it. Maybe that's true, but perhaps the wine has nothing to do whatsoever with Bill not getting colds. Maybe he's got some sort of unusual immune system, or he's like a robot or something. Also, if someone says red wine doesn't prevent colds because I drink it and I still got colds, well, obviously it could be the case that it does help prevent colds, but for some reason it doesn't work on me, or that I do other things that give me colds that the wine can't help. Or as another example, as a runner, whenever somebody dies, unfortunately, in a race, a tragic occurrence, what people always say is, "I'm not going to run. Look at you, you silly runner. This person runs this marathon, they drop dead. I'm just going to sit on my couch and eat Twinkies and Cheetos and watch TV." Well, to say that running causes a heart attack because a few people in marathons have had heart attacks hardly proves it. In fact, the reason why it makes the news is because it's so unusual. You generally don't hear in the news someone who smoked, drank, overate, never exercised, had a heart attack today. Doesn't make the news because it's not unusual or extraordinary. And so those would be examples of appeal to anecdote. Now, to establish something as a causal factor, to say that X is a causal factor for Y, what we have to do is to show that there would be more cases of Y if everyone was exposed to or did X than if no one did. And you can't show this or demonstrate that X isn't a causal factor for Y by citing an example or two. It's not about an example or two that's an exception or unusual. It's about the whole population. But again, take the example of smoking. If someone says, yeah, all this studies about smoking causes cancer is BS. My aunt, Hilda smoked, 30 cigars a day for 90 years, and she lived to be 110. So it's all BS. Well, when we say smoking causes cancer, we don't mean that if you smoke, you get cancer. We don't mean that if you don't smoke, you won't get cancer. It just means that if everybody started smoking, there'd be more cancer than if no one did. And of course, that's perfectly consistent with some people smoking and not getting cancer, and some people not smoking and getting cancer. It's exactly what we would expect. Final mistake: confusing explanations with excuses. Now, it must be kept in mind that not all explanations are attempts to provide an excuse. For example, a person might explain why the United States often acted on racist policies without any intention of justifying them. So a person might say, like in World War II, the Japanese internment took place because of fears and concerns about the Japanese and the racism in America. But of course, the person explaining that need not be justifying it. Similarly, a person might explain why slavery was tolerated for so long in the United States without justifying it, simply saying this is not why it was correct, which obviously it wasn't, but why it did occur. And people sometimes make that mistake. For example, in the case of the 9/11 attacks, some academics attempted to say why this occurred. They weren't trying to justify it, they were trying to explain it. And they were accused of trying to justify it. Because they said, for example, the attack occurred because of as a response to American foreign policy. They didn't say the attack was thus justified, they were simply saying why it occurred. And so the fallacy is this, is to assume without justification that someone who's trying to explain something, the cause of bad behavior, is trying to excuse it. The mere fact that someone is trying to explain something does not entail they're trying to justify it. What's the difference? Well, explaining it is saying how or why it occurred. Justifying it is basically saying that it was correct. So, for example, a person might explain why we're using drones to assassinate people in the following way. They might say, well, the reason why it's being done is because, first, it's regarded as putting fewer American lives at risk. Secondly, it's regarded as a fairly cheap option in terms of going and killing people. You simply send your drone and it drops a hellfire missile on someone, and boom, they're dead, rather than having to go on the ground, risking lives and expending many more resources. Now, of course, that's not intended to justify it. It's simply explaining why people do this, because it's cheaper and safer than sending in troops. Now, if someone says, because it is cheaper and safer than sending in troops, it is therefore acceptable morally to do, that would be justifying, as opposed to simply saying why people do it, saying that it is a correct thing to do. And that brings us to the end of mistakes in causal reasoning. And next, we'll turn to causation and the law.